Good afternoon.
Hey, good afternoon. So
How are you, sir?
I'm good, good. How is it going? I mean, I hope the participants are
Yes,
comfortable.
participants are comfortable. Yes, very much as usual, sir. Now, I think we should say as usual.
Thank you so much. Yeah.
Very informative session, sir. So I think with your due permission, we shall just wait for 2-3 minutes more so that more participants would join.
Sure,
Okay.
sure.
Okay. Thank you so much.
So, can you also share some photographs with me if you have taken?
Yes, sir. Sir. So after
So
this
you can
session,
send.
I'll share. Yes.
Yeah, sure. You can send it in my WhatsApp.
Yes. I will. I will. I think, sir, we can resume the session.
Yeah, sure. Okay. So good afternoon, and I'm going to share the PPT again. Okay, so what I'm going to do is now I'm going to use the same data and going to tell you something about another functional form. We understood linear equation. We also understood the logarithmic application in the functional form. So two different applications we have understood, and we also have understood the interpretations. Now this is the third one I'm going to tell, and after that I'm going to go to the multiple regression. So here the formulation is quadratic in nature. So you have the y is equal to beta 0 plus beta 1x plus beta 2x1 square and plus e. So this formulation you can see here has got one extra calculations, which is x square. It's the same variable. It's not a different variable, but this variable has been squared up. Now squaring up actually helps us in many ways because it also tells us the rate of change of the curve. And then it gives us the two different slopes. So you can see one slope is represented by beta 1, which is a linear slope because it has got only x, and beta 2 represents another slope, which is squared up. So it actually tells us the rate of change over time. So it actually presents a different slope. So there are two slopes combined in the same curve. So you must have come across this kind of curve, which is basically quadratic with a one turning point. But if you add another, make it cubic, then you will get two turning point in the same curve. So these kind of formulations are very useful, especially in the population analysis, or especially in the analysis where you are looking for a turning point. So maybe, as simplistic as analysis of simple linear regression does not help us in many situations. For example, the data which I have shared with you about the market companies and how they are spending money on their advertisement and how their advertisements are effective in the market promoting sales. Here, any manager or person in charge would like to have two kind of decisions. If they are thinking about the budget to be decided for the next year, whether how much to be spent on advertisement or not. So there are two kind of questions that he would like to face. One question would be regarding uh, does it really make sense for him to spend money on advertisement? So that's the one question that he would like to have the answer for. Uh, is it useful? It's not so useful. Second question, given the market conditions, of course, market scenario. And second question is like to confront is if he has decided to spend money on expenditure, so given this whole entire market scenario, how much money he should spare for the next year on advertisement? Is there any optimum amount that he should be talking about? So if you really want to be interested in finding out the optimum amount to be spent, then the simple regression is not going to help you. Here you have to go for finding the turning point. Because in turning point, we all know simple algebra that the first order conditions are you first derivative you take out, make it equal to 0, and the second derivative is either negative or positive. If it is positive, then you get a lower turning point, as in the case of cost analysis or some other area where you're looking for some lower turning point. Or if if you're dealing with the GDP data, let's say for the whole economy, you are interested in when is the turf occurring, or when has the recession or recession occurred, and when is the recovery going to happen. So these kind of questions you can work out if the second beta is giving you a positive turning point, that is the second derivative is positive. But if the second derivative is negative, uh, that means the curve is going to give you an upper turning point. So the curve is going to increase, and then it will reach the peak, and then it will come down. So here in this case, what we are looking for is the upper turning point, because we are interested in knowing what is the optimum expenditure, what is the maximum expenditure that one should actually do on advertisement. In a way, we are trying to find out that is there any optimum level of expenditure where the impression retained for that advertisement actually gets maximized for the customers. Uh, or in a way, we are also saying that is there any expenditure level beyond which it's a wastage to make expenditure on advertisement, because the nature of advertisement is such that you keep on spending money and it will keep on increasing the effectiveness of expenditure, effectiveness of advertisement. It doesn't happen that way. So the marketing theory says that at some point of time, the saturation will occur. Either you have to change your advertisement or you have to make some amendments in that in order to make it more effective, because it does not remain that effective when you started with. There are hardly fewer, couple of advertisement that we have come across in our lifetime, which has become permanently effective, but not most of the advertisement. So we are looking for upper turning point. So here in this data, I'm going to show you how we have actually used this quadratic equation. So I'm going to go and take you to the data again. So you have the data in front of you. These are the forms we have already seen. Then this is the impression data, then the expenditure data. So all we need is one more data, which is expenditure square, in order to make it x square. So we are going to go to transform. We all know how we create a new variable. So here we are looking for expenditure square. So we'll say, okay, exp2 should be the name of my variable. And the argument I'm going to build is probably expenditure multiplied by expenditure. So what I'm saying is that you multiply expenditure with expenditure, give us expenditure square. And then we say, okay, and if we go to the original data set, you have the variable already created. So now you have got two variables, one is expenditure and another is expenditure square, to be put on the right hand side of the equation. So we go to analyze, go to regression, go to linear. Resetting is always good because it gives you you don't remember everything that you have put in over there. So impression is dependent, and we have the expenditure and expenditure square. These two variables are independent. So we have now the equation, which is reading like y is equal to beta 0 plus beta 1x plus beta 2x square. And then we say, okay, and this is the result we have got. So we see here that the R square, adjusted R square is 0.47, which is not a very strong model, but F is, significant. So we'll go by this equation. And then here is the coefficient. The coefficient reads like, y is equal to 7.057 is the constant. Then plus 1.085 is the beta 1 coefficient. And the second coefficient, that is the coefficient for square, is minus 0.004. So we can see that there are two kinds of sign that we got in this equation. The first sign we got is positive, which is for beta 1. So positive sign for beta 1 means that the linear side of the curve is upward sloping. So it's going up. So this answers the question that yes, it makes sense for spending money on advertisement, because advertisement and impression curve is going up. So it's a positive relationship, and we need to spend money on advertisement. It is going to result some result, good result. Second, the beta 2 is negative. That means the second derivative is going to give us negative. So it's a turning point. So the curve is going up and up, and at certain point of time, it is going to peak, and then after that, it is going to go down. So if you look at this equation, I've written the equation over here. The quadratic equation is, this is the linear equation. So I'm right, quadratic equation is here. So 7.059 plus 1.085 expenditure minus 0.004 expenditure square. So that's what the equation is. And if you can use the derivative here, so DIMP divided by DEXP. So you're finding out the dy by dx in terms of DIMP, impression, with respect to expenditure. So if you do that, one who knows the calculus will understand this. So this turns out to be 0, and 1.085 minus this 0.002 becomes 0.008 after we do the derivation. So first derivative is equal to 0. We make it equal to 0 for maximization or minimization conditions. And here we get the expenditure equal to 135 by calculations. So this means in this particular market, any expenditure that we decide on advertisement will work till 135.625, whatever is the expression. So we should not spend more than this amount. That's what it is suggesting.
I mean, we implemented new connection.
Yeah. So this is the uses of a quadratic equation. There is another way to look at all these. I'll just show you. This is very interesting. So go to regression, and instead of going to linear, go to curve estimation. So there is a button over here. You can see that curve estimation. So when you go to curve estimation, it's going to ask you what is your dependent variable. So we'll say, okay, my dependent variable is IMP, which is your independent variable. So we'll say, okay, my independent variable is EXP. And then it is asking, do you want a constant to be included in the equation? I said yes. And then do you want to plot the model? Then I said yes. It's already by default. Linear is already by default. So which equation you want to estimate? So are you interested in linear? Are you interested in quadratic? Are you interested in, let's say, cubic, logarithmic? So all these options are here, as these are very interesting options. So state-of-the-art options. So I have clicked quadratic and linear and said, okay. So I don't have to convert the data or create any other variable. So here, quadratic equation is already, estimated, even without converting exp into exp square. And you can see here, quadratic, first is linear, second is quadratic. So R square is 0.53, F degree of freedom, significance 0.001, and the parameters, if you see constant 7.059, the same parameter we got for beta 0, and this is for beta 1, 1.085, and this is for second beta, that is for the square. It is minus 0.004. So you get the same equation over here, and then additionally you get this graph. So this graph actually shows that if you look at the linear, it's going up, and quadratic has got two slopes. One, it is actually going up, 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 and up, and this is the place where it reaches the peak, and after that it starts falling down. So your beta 2 is negative. This shows that the curve is going to go down after reaching the peak. So it gives you the upper turning point. So your upper turning point arrives somewhere here. And if you draw a parallel line, just to see by rough estimation, it will touch the x-axis somewhere around 135. So that is the rough estimation of optimum amount of expenditure you can make out of these calculations. So I showed you two things from this data. One is you can directly calculate the expenditure elasticity, or for that matter, if the data pertains to cost, data pertains to any other variable that you're looking for, you can directly calculate the elasticity from using the double log formulations, which is a very useful formulations. And this one is where you get the turning point. So this serves another purpose for you. So these are the two applications of the quadratic equation. So what I have spoken so far in regression is, one, I have spoken about simple regression. Then I have spoken about double log regression. Third, I have given you some applications of quadratic equation. In the meanwhile, I also spoke about the problem of heteroscedasticity and what to do if the problem of heteroscedasticity occurs. So these are the coverage I have made for regression, which is simple regression. So we'll be moving to multiple regression now, but before that, if you have any question.
सर हम सिंगल लॉग भी ले सकते हैं कि सिर्फ एक वेरिएबल पे लॉग लगा लें? Is it possible?
हाँ, possible है. वो उसको हम लोग semi log बोलते हैं. So there are two formulations. One is called semi log, another is called double log. So in semi log, you can take one of the variable as log, and this the other variable will not be in the log, but the interpretation will change in that case.
Okay. तो सर जो वेरिएबल वीक दिख रहा है जिसका सिग्निफिकेंस कम लग रहा है, अगर हम उसका लॉग ले और बाकी का ना ले तो और उसको सिग्निफिकेंट कर दे इस तरह से, तो एक्सेप्टेबल है मॉडल में?
So the logic for log does not flow from what you have said. The logic for log will flow from two things. One, if your data has got variability and you want to check the variability or control the variability, so you convert that into log. That's one logic. Another logic for converting into log would be that if your data has got growth trend, like you're looking for growth trend. For example, if you have a income growth, GDP growth, stock market data, you cannot use log so frequently because it doesn't show you the growth trend. It has a sporadic movement. So you can go for some other kind of, estimations from that data. So, but not the logarithm is not going to help you much over there. So anything which has got inbuilt growth into it, just sales data, for example, so is very much qualified to be converted into log. So that is another logic. Third could be that if you have a special interest in finding out the elasticity directly, then you can use log. So these are some of the considerations for using the log.
Okay, got it, sir. Thank you.
Sure. All right, so let's move forward and let me open another data for you. So this time I'm going for the car sale data. So I'm opening this car market data. Right, so you can see here, these are the manufacturers, these are the models of car, sales, the resale value, price, engine size, horsepower, wheelbase, width, length, curb weight, fuel capacity, fuel efficiency, and log sales. So these are a lot of data which is there for the car market. And in order to give you an idea about this car market, how it looks like, let's go to the plotting of the whole data. And here we are going to take two variables. So one, let's take sales on the one axis, sale, and we are interested in modeling the sales. And there are many factors which is going to affect the sale. The price is one of the factor. But for the sake of curiosity, we are going to take fuel efficiency, let's say, as a factor affecting the sale. So on the other hand, I'm taking fuel efficiency. And then I'm also interested in knowing which car models they are talking about. So I'm bringing the model as a point level variable, and then I'm saying, okay, just take a look at the graph. This is the market in front of you. It gives you the bird overview of the market. You can see all the cars are behaving almost in the same manner over here, except these two exceptions that you have in the car market. So one exception is F series, another exception is Metro. So what is the difference between these two cars? And these two are at two different ends of the spectrum, you can see. So F series is a car which is actually being sold in the market quite a lot. There is a huge sale. It's one of the highest sale in the market, but on the fuel efficiency, it's one of the lowest, the F series. But if you look at the Metro, it is very high on fuel efficiency, is the highest in the market. But if you look at the sale wise, is very low, is one of the lowest. So these two are the outliers in this whole data set. But if you start running regression on the base of this data without doing anything about this data, you will be in trouble because your betas are going to be either very insignificant, most of it is going to be insignificant, and you're not going to get the right kind of result which you are expecting. For example, if I just show you the result, so if I go to regression, go to linear, and then try to model the sale based on, let's say, all these kind of factors, price, engine size, horsepower, wheelbase, width, length, curb weight, fuel capacity, fuel efficiency. So I've taken all these factors as independent. So I'm running a multiple regression and then I just want to see the result, how it works out. So here you see adjusted R square is very low, 0.27, which is extremely low, but ANOVA is significant because it says that at least some variables are significant in your model. So model is still usable, though it's not a very high fit or not a very good fit. Which other variable which are coming to be significant? Price, not significant.
No. Engine size is
power,
significant.
engine size significant. Yeah.
Significant.
So let me see the other one. Engine size, horsepower significant.
Significant. Wheelbase is highly significant.
Yes. Width, no.
No.
Width is not. Length is
Length
not.
is not significant.
Curb weight is yes.
Curb weight is significant.
Yes. And fuel capacity?
No, not
no.
significant.
Fuel
and
efficiency?
Fuel efficiency is not significant.
So what does it say about the car market? So it says
like
that
1, 2, 3, 4 variables are significant out of these in this model.
So what does it tell us about the car market?
We need to improve the other variables, and these variables are supporting the model.
Oh, that is fine. So actions to be taken after that. But based on the analysis which is in front of us, what does it say about the car market? What it says is that the people are not price sensitive when they're buying car. That is the first thing they're saying, which is absolutely not acceptable, especially for the Indian market. We are not going to accept this because we all know by all theory and the past information that people are price sensitive, right? Then it is also saying that people are not guided by fuel efficiency. They are not bothered about environmental impact of car, which is also not right, because you look at the higher income segment in our society. They are not bothered about price, but they are more bothered about fuel efficiency, how it is impacting the environment. They are not going to buy the car which is affecting the environment more. So that. So this is saying that the only car which is going to be demanded in the market are going to be big car and sturdy car, sturdy big car, and cheaper car. So people are going for buying cheaper car, big car, sturdy car, right? So they are not bothered about efficiency. They are not bothered about any other thing, or even cheaper car. I mean, we can't be sure because price is not a significant factor. So it's only the big car and the sturdy car, hard car, that is going to be sold in the market, which is not a very good reason to believe that yes, this is a good good analysis of the car market. So we need to examine the data. So we have seen the graph, and if we try to find out the correlation, let's say we do the correlation by this, you can also learn how to do correlation. So by variate correlation, and we are taking the sales data, and then we are taking the efficiency data and trying to find out the Pearson correlation. What we find is that it's terrible, actually. It's negative. So minus 0.17 is the correlation between car sale and the efficiency. That means people are definitely not bothered about the efficiency. They are negatively looking at efficiency, which is not the right thing to do. And then when we looked at the data, we found that Metro and F series, these two are the outliers. So probably our thinking is that either these two, if we remove these two outliers, the data may start behaving well. So what we do is that we go to data. Let me see how to remove this. So we go to select cases, and then we say, okay, if conditions satisfied, and then say if argument we are going to build here, and then we are saying if the model is let me just see, if the model is not equal to Metro. So, you have to put a single quote over there, otherwise it will not take. So we have to remove Metro from there, because Metro is a car which has got high fuel efficiency, but very little sale. So we are interested in, a car which is selling more in the market in order to see which factors is affecting their sales. So F series, I want to keep the F series in the data set. I don't want to remove F series, but I want to remove Metro first, because that's the car which is odd man out. So I'm creating the argument that select the cases where the model is not equal to Metro. And then we say continue, and then say okay. And then how it has affected the data set. If you look at the data set, you will see here that, Chevrolet Metro is checked here in 27th, you can see it's crossed. It's already crossed. This means when the data analysis will be done, Metro will not be taken into account. So it will do the data analysis for all the data set except the Metro. So I go to analyze and see how it has affected the correlation after I removed the Metro. So I have taken sales, and then I have taken fuel efficiency, and then I've said okay. So I calculated the correlation. So here you see the correlation is still negative, but it has improved. So earlier the correlation was minus 0.017. Now it is almost negligible, 0.002. But the correlation is highly insignificant. P value is 0.979. So this is also insignificant, but correlation has definitely improved. So there is something more that we need to do with this data. So another question that comes to us is F series. So because we have left the F series in the data itself, so probably F series is causing the trouble because it's also an outlier. So in order to reduce the variability, because I want to keep F series, I would like to convert the data into log sale and log into the log. And we know how to convert the data into log, so I'm not going to that. The data set already has log calculated. So this is in sale means natural log calculated from the log data. So I'm going to use this one. So go to analyze, then I go to correlation by variate. So instead of sales, I'm going to take log sale. So let's say where is the log transformed? This is log transformed sale. Yeah, log transformed sale, fuel efficiency and log transformed sale. So hopefully, because I've converted the sale data into log, the variability must have gone down and it has taken care of the outlier. So what is the result it has given? Now it has given a positive correlation. From negative, it has come to positive now, positive 0.136, which is a weak correlation, but it's a positive correlation. But it is still insignificant because the p-value is 0.09. So it's more than 5%, right? So it is still insignificant. But the thing is that the variability must have been controlled by using this log, and that's the reason why this is happening. So the question is, what else can be done? So, since it is a car market data, the interesting point to be noted here is that this also reports the car in two segments. One is for the LMV section, like car uses, the domestic uses of car, which you and I buy, and other was the truck section, so which is used for the transportation and goods. So probably, I need to look at how the market is divided over these two segments. So I'm going to, I'm going to look at the market once again. So I've kept, let's say I'm going to keep the log transformed sale, not the sale. So I'm taking the log transformed sale here and fuel efficiency. And then I'm saying that stack the variables or stack the data by setting two different colors on the basis of vehicle type, right? So it will differentiate the entire data. It will differentiate the entire data into two color, which will actually reports the domestic use car and also the truck separately. So it will give you a visual appearance of how the market looks like between these two segments. And if you look at these two segments, you can see that the blue colors are all on the one side and the greens are all on the other side. So this means there is a sharp division in this market. In order to look at this again very properly, let me just make one more changes. So let me keep log here and the fuel efficiency on just changing the axis so that you can have a better view. Fuel efficiency on x-axis. So this will give you a better view. Now, see this. This is a wonderful view. So you can see the green dots are on the one side, the blue dots are on the other side. So this whole car market is divided into, but if you calculate single correlation by adding these two kinds of car together, probably that is a problem, because fuel efficiency mindset is not the same in the two segments. So let's divide this data. So what I'm doing is that I'm going to data and then I'm saying split the file. So I'm going to split the file now, and I'm saying organize output by group, and the group needs to be based on the vehicle type. So what I'm asking is that calculate the output separately for the vehicle types. And then I said, okay. And then now the data has been divided. I'm going to go to correlation, reset. Then I'm taking log transform sale, the fuel efficiency. And then I'm saying, okay. So here, the vehicle type is automobile. And this is the correlation, and this is the vehicle type truck, and this is the correlation. So if you look at the automobile, the correlation is 0.451, and this is significant. So it's positive, moderately positive, and significant. But in the truck segment, you can see 0.203, and which is not significant. The p-value is 0.21. So this means while it comes to purchase of the truck, the consideration of fuel efficiency is not there. The environmental concerns are not there. But when it comes to automobile purchase for the domestic uses, there is moderate considerations for the fuel, efficiency. So this is how it works, right? So this is to give you a glimpse of the entire car market. Let me revert back to the entire file, analyze all cases. So I have to get back to the original data. So I'm just removing everything I have done. So split the file. So I'm not also splitting the file. Analyze all cases. Do not create groups. Okay, this we have already done. So let me just see. Select cases. So select all cases. So now my data has gone back to its original position, right? So now I'm going to regression. Going to regression and going to linear. And now I'm going to go to stepwise regression, right? So let me reset the whole thing first. Sales, so I'm taking the original sales data, not the log sales. And then I'm doing the work on the original data. So these are the variables. Now I'm going to work out the regression on the basis of stepwise method, right? And stepwise regression, estimate, model, and then I'm also saying that give me collinearity diagnostic, right? So collinearity is a problem which indicates that your independent variables themselves are correlated with each other. And one of the assumptions of regression analysis is that it should not have a multicollinearity problem. Multicollinearity problem is when your independent variables themselves are correlated, because the same thing, the problem it gives is that the same thing which has explained y is now being explained by another variable. So is the multiple explanation of y is coming from the same thing time and again from different variables. So that means it will inflate your beta quite high. So if multicollinearity exists in your problem, in your data set, your predictions are going to shoot off in one direction. So it's not going to give you a very good picture. So for that, we need to do stepwise analysis. The stepwise regression, what it does is that it actually go for the iteration process, and it picks up the best variable in the first iteration, and then it does another iteration on the rest of the variables, and then again it picks up the best variable from there in the second iteration, then it will go to the third iteration. So likewise, it will keep on iterating till the point it gets the variables which is free from the collinearity problem. And therefore, in this case, we found that it has actually taken the second. It has actually done the 2 times iteration. So in the second iteration, it got the best model. So all we have to do is to analyze the second model. So in the second model, we see that there are 2 variables that it has picked up. One is wheelbase, another is price in 1,000. So these are the two variables it found to be significant and also non-correlated. So it doesn't present any collinearity problem. For example, if you look at the collinearity statistics, there are 2 parameters that you have to look at. One is called the tolerance, other is called the VIF. VIF is a variance inflated factor. So in any case, if your variance inflated factor is more than 2, it indicates the presence of multicollinearity. And if your tolerance is very low, it will actually reflect the problem of multicollinearity. So if the tolerance is maximum, will go up to 1. So nearer the 1, the better, better the case. And VIF, lower the VIF is better the case. So it should not be more than 2, and in tolerance, it should not be less than, let's say, 7.7 or maybe 0.5 or 0.2 or 0.3, something of this. So here, the collinearity diagnostic suggests that there is no collinearity exists, multicollinearity exists, if these 2 factors are picked up for analysis. I'll just give you a contrast. So let me go back again and do the simple correlation, simple regression, and then ask for the collinearity diagnostic. So in the simple correlation, when you look at the collinearity diagnostic, so this is your collinearity diagnostic in simple regression. It's not a stepwise. So here you see the VIF is all 4, 6, 8, 4, 3, 4, 7, 4, 4. It's all more than 2. And here the tolerance is very low, 0.2, 0.1, 0.3, like this. So you can see here very clearly that it has a serious problem of collinearity. Another way to look at collinearity for any researcher is that you pick up all the independent variable and run a simple correlation matrix. So when you present that correlation matrix in front of you among the independent variable, and if you find that most of them have significant correlation, turns out to be significant correlation at 5% or 1% level, this means they have multicollinearity problem. That's also one way to look at. But you can also go to collinearity diagnostics and understand what collinearity is all about. But here you see this is the model, and without any collinearity is the second model that has been estimated. How the process of variable exclusion happened, just to give you an idea about that, they have looked at these the software has looked at the partial correlation for selection criteria as selection criteria. Say, for example, in the first case, wheelbase was picked up. And in the second, it is the price which was picked up. So if you look at the wheelbase, let me just so in the first model, if you look at either excluded variable, the first model, if you look at here the price in the first model, the wheelbase was based on the best variable that they could pick up, and in the second, the price was picked up because here you see the partial correlation of price is the highest in all the partial correlations you can see here. So after excluding the wheelbase, you have the partial correlation of 0.36 for price, and rest of the partial correlations are lower than 0.36. So this is the highest partial correlation, and that's why price was picked up. And after the price was picked up, this is the correlations. You can see all the correlations are very low partial correlation, 0.09, 0.03, 0.02, 0.05. So it did not qualify for any selection, and partial correlation actually indicates that what is the amount of influence this particular factor is having given the other factors as constant. So price does have an impact on the explanatory variable, and that's why it was picked up as a significant variable. So here, this was the criteria on which it was selected. So wheelbase, you can see, and price, these two variables were selected. And if you look at their parameters, they are significant over here. You can see the unstandardized beta is here, standard error, then t value, then p value. P value, in both the cases, the p value is 0.00000. So they are the best variable without any multicollinearity in the model. So what does it now say about the car model? It says that people are looking for a bigger car wheelbase. This means bigger car and a cheaper car. Earlier conclusion was that people were looking for bigger car and sturdy car, and they're not bothered about the price or the fuel efficiency. Here, fuel efficiency did not work out to be a significant variable, but what it makes out is that your bigger car and the cheaper car is the call of the market. So people actually do look for that. Any questions on this collinearity or any other question or multiple regression?
Sir,
STS,
could you
sir.
please, excuse me, sir, could you please repeat the steps to remove outliers?
Okay, so you want me to calculate again, or you want me to explain again?
Only 1-2 steps in SPSS.
Steps. Okay, so you go to analyze, go to regression,
अच्छा ठीक है अभी दे दी अभी आ रहा हूँ
go to analyze, go to regression, go to linear, then insert the variables. Like dependent variable we have is sale, and we have the independent variable that is price, engine size, horsepower, wheelbase, width, length, curve weight, fuel capacity, fuel efficiency. So these are the independent variables. So this is what we have done. Then we go to method. So there is a button here, you can see. It's a drop down window. From here you can select stepwise, right? So there are other methods also, backward, forward, but we selected stepwise. Then we go to click this button, statistics. Here you can see the estimates and the model fit is already checked. But if you really want to see the collinearity diagnostic, then you can actually check that. If you want to calculate Durbin Watson, some other, so there is a lot of diagnostic that you can do. So if you want to see the residual analysis, you can also do the residual analysis by clicking this. So it will give you unstandardized residual error terms, and then you can also check whether the data has any heteroscedasticity or not. And then you can say, okay, and then you get all these results, right?
Sir, how to remove outliers from the existing data?
So all you have to do is to remove the data.
Yes, only how to remove outliers from the existing.
So you have to identify which which
Yes.
case is your
In any case, you practiced that how to remove the data of metro.
how did I remove
That
the data? Okay.
yes, yes. In the case of metro.
Okay, so I had gone to data. So there is a button called data, right? So here is a drop down window. You can see here down there. It said select cases. So there are two. One is called the split cases and split file, and then it says select cases. So I clicked these select cases. Okay, so I did that, and then I clicked this argument if condition is satisfied, right? And then I click this button. So this is the argument which I put over there. If model is not equal to metro. So I said select all the cases except metro. So that's how the argument was built. Did you get the point? Should I do it again?
Yes, sir. Thank you.
Yeah. So just to give you, another round. So go to data, go to select cases, click if condition is satisfied, then you click this button if, and build the model, build the argument over there. And then if you say continue and okay, go back to your data set, and then you will see that it has been separated. So now you can see this 26th is separated, right? Metro has been deleted from there. So it will not consider metro once it is doing the analysis. Is that okay?
Thank you, sir.
Any more question? All right, so shall we move forward?
Yes, sir, we can move forward.
Okay, let me just see. So now I'm going to go to this one. So we are going to talk about the dummy regression now. So it's a special case of regression analysis, and it's quite useful. So I'm going to tell you something about the dummy regression. So in dummy regression, you have the dependent variable, and the explanatory variables are categorical in nature, right? So you have, let's say, gender as independent variable, or different regions as independent variable, any category, occupations as independent variable. But your dependent variable is a scale variable. Say, for example, you want to estimate the regression impact of occupation on income of people. So you have the income data, which is the dependent variable, which is a scale variable, but your independent variable is different categories of occupation. So agriculture, service, and others, something of this sort. So this is the typical case of dummy regression. So I'm going to give you a data of dummy regression just to have a look at that, and then we'll proceed further. So I'm fetching the data. So I'm fetching the data from Excel sheet. And I know the data, so I have noted down the range which I have to import. So this range is A1 to E52 in the data set on seat 1. And I'm saying okay, and the data is in front of me. So this data is about the different region. You can see here north, then it is followed by south, then it is followed by west. So there are 3 regions. And next data is about the average salary. So average salary in these regions. So this is the data about average salary to the teachers. The third data is about the spending which is done by the government on these schools. So this is the government spending on these schools, average government spending. Now here, what we are interested in is to know whether there is a regional difference in the salary of the teachers. So this is what, and we want to use regression to understand that. So normally, the categories of north, south, and west, we can actually ascertain some kind of ANOVA, and we can understand that, or maybe by using simple chi-square, we can understand that. But we want to use regression to understand it. This is a very handy tool for this kind of analysis. So for this, we have to create dummy variable. So how the dummy is created? So here there are 3 categories of regions, north, south, and west. So 3 minus 1, we have created 2 dummies. So if you have 5 regions or 5 categories, then 5 minus 1, you will have to create 4 dummies. So something of that sort. So this is how you create the dummies. Number of regions or number of categories minus 1. So why we do minus 1 is because in your regression equation, if you keep the intercept, then the number of dummies that you create has to be minus 1. Number of categories minus 1. But if you create dummies as many as the categories are, if there are 3 regions and if I create 3 dummies, in that case, I have to remove the intercept from my equation. So I don't have to keep intercept in my equation. If I keep intercept in my equation, then it will become a case of perfect collinearity, and you will not get any result out of it. So regression will collapse. So because the intercept represents the dummy, which is called the reference dummy. So we have to actually select one dummy, which is going to be called the reference dummy. So let's go to this. Let me just show you that. So here, the process of dummy creation is like this. So we have taken, let's say, north, south, and west. So we have taken west as a reference dummy, right? So if I have to, the reference dummy is west. So if west is my reference dummy, that is, I'm going to compare west with the other regions. So if west is my reference dummy, then the dummy for the north can be created like this, that we'll put the value 1 if it is north and 0 if it is not north. That means all the north regions, I'll put 1, 1, 1. And for the regions which is not north, maybe in the south and west, I'll put 0, 0, 0. So that becomes the dummy for the north. And your main equation of the dummy regression is going to be like this: y is equal to beta 0 plus beta 1 dummy 1 plus beta 2 dummy 2 plus e. So this is the main equation. And if I try to find out the average for the north by creating this kind of dummy, then the expected value of y for north has to be when the dummy 1 is equal to 1, because we are considering north dummy. So dummy has to be 1, and the second dummy D2 has to be put to 0. So if we replace D1 by 1 and D2 by 0, then our yi is going to be equal to beta 0 plus beta 1. So that means these two coefficients, the two parameters, beta 0, that is intercept, plus the regression coefficient of dummy 1. If you add these two beta, these two beta will give you the average salary of the north, right? Likewise, if you are creating the dummy for the south, that is D2, so we'll put 1 for the south and 0 for the other two regions. And in that case, the expected value of y, that is average for y, will be when we put D1 is equal to 0 and D2 is equal to 1. So in the same equation here, the regression equation, if you put D1 is equal to 0 and D2 is equal to 1, then you will have you'll be left with beta 0 and beta 2. So here your equation for the average that we are going to see for the salary is going to be beta 0 plus beta 2. So that's the average for the south, right? And what will be the average for the west, which is a reference dummy? So here we are not creating any dummy for the west. So both the dummies we are putting at 0, 0, 0. So if you put 0, 0 in the equation, then we are left with y is equal to beta 0. So intercept, y becomes intercept. So intercept becomes the average for the west. And that's why I said in the beginning that we are creating dummy, number of dummies as category -1. So there are 3 categories. So we are creating 2 dummies. These are the average salary calculated from the data and put in over here. So I'll just show you the calculation of average salary for the 3 regions. So if I have to calculate the average salary for the north, so I'm creating a data for the north. So I'm taking these salaries for the north. So north salary is till this point. So I'm just copying this and putting it over here and calling it north. So there is another variable I have created as north, and these are the salaries for the north. Then for south, I'm copying from here. So these are the data for the south. Naming it south. Then for the third category, west, starts from here till this point. Naming it west. Now I'll give you a simple calculation of the average. So we go to descriptive. I'm taking north, south, west. I don't want standard deviation, minimum, maximum. I just want mean. So okay. So this is the average value, average salary in the 3 regions, north, south, and west. This is exactly what has been reproduced here. So 24,424, 22,894, and 26,158. So if you can see here, this is what has been reproduced over here. So I've just noted down all the salaries in front of you, right? So I'm going to go back again and calculate the regression. So have you understood the process of formulating the dummy so that I can go and calculate the regression? Okay, so you go to analyze, regression, linear. So here my dependent variable is salary, and my independent variable is these two dummies we have created, right? And then I'm saying okay. So not a very strong fit, poor fit, and the F test is also not very significant. But let's see the coefficient for our understanding. So the constant is 26,158, and the D1 is minus 1734, and D2 beta is minus 3264, right? So we go back to this result. So here you see beta 0, we got 26,158, and beta 1 was minus 1,734 for D1, and beta 2 was minus 3,264 for D2. So by using the logic that we created earlier, the average for the north. So the average for the north was beta 0 plus beta 1. So if you take the value of beta 0 to 26,158 and take the value of beta 1, so beta 1 is minus 1734. So minus 1734, it gives us 24,424. And if we go back to see what was the simple average for the north, it was 24,424. And here, by using the regression equation, we got the same figure, 24,424. So this means that the beta 1, which is for north dummy, is a differential beta. It is not an absolute beta. So the beta of the dummy variable is different in interpretation in comparison to the beta of the simple regression. In simple regression, the interpretation is that it shows the rate of change or something like that. But here, it actually represents the difference. It's called the differential dummy. Why? Because it shows by how much amount the figure for north is different from different in comparison to the reference figure. So reference dummy in our case was west. So how it is different from the west? So it is 1,734 different from the west. So that's why the average for the north is 24,424. Likewise, average for the south. And we have seen in the previous slide, beta 0 plus beta 2. And here the value of beta 2 is 3,264. So again, beta 2 is a differential beta because it tells us by how much the salary, average salary in the south is different from the west. So it is different by 3,264. So you can see the average salary in the south, 22,894. And here earlier, when we calculated the average salary of the south, it is 22,894. So where is the average salary of west? We all know that west is a reference dummy, and we have not created any separate dummy for that because it is the intercept which represents the west, right? So intercept is beta 0, and the value of beta 0 is 26,158. And if you look at the average for the west is 26,158, right? So this is the basis of calling why the dummies dummies beta, they are the differential beta. They are not the absolute beta. Now the question is that if north has a difference of 1,734 rupees and south has a difference of 3,264 rupees in comparison to west, whether these differences are significant or not significant. If they are not significant, this means the difference between the two regions are immaterial, But if this is significant, then the difference between the two regions are material, or it matters. So here we see that the D1 differential coefficient is not significant because the p-value is 0.233. So it's pretty high, right? More than 0.05. And D2 differential is 3,264. And here the p-value is
significant.
Less than 0.05. So it is significant. This means that the people in the South are getting significantly different salary in comparison to West, while the people in the North and the people in the West, they are not getting significantly different salary. So any difference that appears to be there is by chance, but not a significant difference. So this is the conclusion based on this table. This is very simple to understand. The only issue over here is to formulate the dummy. So if you are able to, or you're well versed in formulating the dummy, you can do it. So for example, here in dummy 1, the north dummy is 1 1 1 1 1. You can see here we have put all 1 1 for the north, and when it comes to south and west, they are all put equal to 0 0 0 0 0. So it becomes the dummy for the north. Likewise, when we created the dummy for the south, then north becomes 0 0 0 0 0, and south becomes 1 1 1 because it's a dummy for the south, and then west becomes 0 0 0 0, right? So these are the two dummies that we have created. So easy process to create dummy. Any question before we move to another application of dummy? Any further question? Okay, so we go to file, open. I'm going to open another data set. Excel, dummy variable, open. So this time I'm going to open the data set from C2. And the range I'm looking forward to is A1 to D27. Before that, there's one more thing that I left. So let me finish that. So we also have spending as a data. So probably the salary given in different regions are also affected by the public spending. Because if the public spending is more, then the salary is likely to be more. So we can also use spending as a covariate, right? And it is possible to create a regression equation which has dummy at the same time a variable. So I'm going to do that. So we go to analyze, regression, linear, and here spending is used as a covariate. So here you have a variable on the right hand side, at the same time two dummies. So two dummies along with a variable. So it works as a covariate. So this means there will be an impact of this variable on the relative positioning of the beta, right? And your conclusion may go different if you consider that as consider additional covariate. So here you can see the adjusted R square has improved 0.7, so it looks good. F is significant, definitely. And here, when we accounted for the spending, the beta coefficient is 3.289. So this clearly shows that if the government spending is increased by 1, then the salary is affected by 3.2. So that is something, some interpretation that we can do over here. And if you look at the dummy 1, The dummy one is significant. Dummy 2 is not significant. So it actually changes the result. And it says that controlling for the government spending or looking at the government spending, the North people are getting a different salary in comparison to West, while South people are not getting this different salary. They're getting the same salary. So probably the difference is not significant for North in comparison to West. The difference is significant for North in comparison to West, not for South. Sorry, so just the result actually got changed when we use the covariate. So the point over here is that in dummy regression equation, you can always use a covariate. You can also use some variable and dummy both. So that makes it very interesting. So let me now go back to the new data set. So here is a new data set. You'll find this application a little interesting. So this data set is about the savings data over a period of time. So the data is from 1970 till 1995. So it's a time series data. And then you have the data for savings in some unit, and then you have the data for income. Now here, the problem at hand is that, let me just go back to this slide. Yeah. So here the equation that we are looking for is this. So y is equal to alpha 0 plus alpha 1 dt. That means one dummy we have created over here. Then beta 1 xt. Xt is the variate that we are using here. And then beta 2, we are using the interactive dummy. We call it interactive dummy. So d into x. D into x means dummy multiplied by the variate is an interactive dummy that we have created. Why? Because here the problem is that we want to divide this whole observation into two time frame. One is from 1970 to 1981, and the other one is from 1982 to 1995. And we want to see if there is any significant behavioral change that has happened in the saving behavior of people. So this kind of problem may occur. For example, you want to understand how the stock market behaved in pre-pandemic era and post-pandemic era. So 2020 becomes the dividing year, and 2020 is a major dividing year. It has affected a lot of behavior. It has affected the behavior of saving. It has affected the behavior of purchase. It has affected the stock market functioning. So it's a major change. So you can use the 2020 as the dividing year. And if you have the data for previous years and post 2020 years, you can try and find out the difference. Here in this case, if 1981 was the dividing year, then from 1970 to 81, maybe some government may have come up with some kind of new policy towards saving and taxes that might have, the researcher may have the interest to know how it has affected the saving behavior of the people, of that policy actions by the government, which was taken in 1981. So 1970 to 81 is one period, and 1982 to 1985 another period. And we want to know how the changes have happened during the two period. For this, the dummy can be used for this kind of analysis. And this is the equation that you have to create. You have to create one dummy, and the dummy can be created like this, where you have the one for the observation in 1982 to 1985. So you divided the 2 period, and the second period is considered as for the dummy, and the first period is a reference period. So from 1982 to 95, we'll put 1 if the observation belongs to 1982 to 1985, the second period, and we'll put 0 otherwise, that is for the observation, which is from 1970 to 1981. So any observation from 1970 to 81, we'll put the value 0, 0, 0, 0. And any observation from 1982 to 1985 will put the value 1, 1, 1, 1, 1. So that is the dummy we are creating by dividing this whole time series into 2 segments, right? So that's how the dummy is to be created. Now there can be 4 different, scenario that we may observe. So when we are talking about the change in behavior, there are 2 things that we are talking about. One we are talking about is the change in the quantum, in behavior in terms of quantum change. Say, for example, people were saving earlier more, and now people are saving less. So this is a quantum change. Second, we are talking about is a behavioral change. So there is a structural change in the mindset of the people towards the saving, right? After this particular period, or after this policy action, or after this event, there is a structural change in the mindset of the people. Now, these 2 are captured in the regression equation by the 2 beta. So the intercept beta 0 captures the quantum, and the slope beta, that is beta 1, it captures the behavioral part. So there can be 4 different scenarios that can emerge. The first can be called the coincidental regression. The coincidental regression is the one where you can see that if you divide the time into 2 periods, and one is represented by alpha 0, that is the intercept of the first period, and beta 0, the intercept of the second period. So for the first period and the second period, the intercepts are the same. And for the first period and the second period, the slopes are also the same. So alpha 1 is equal to beta 1, and alpha 0 is equal to beta 0. So you have the single regression equation, which actually represents the scenario of both the periods, before and after. And if that happens, there is absolutely no change, either in behavior or in quantum. That's called the coincidental regression. Second is called the parallel regression. So what is happening here? So in parallel regression, alpha 0 and beta 0 are different. So these 2 curves have 2 different origins, you can see. So their origins are 2 different places. So that means the slopes are different. While if you look at the, the intercepts are different. While you look at the slope remains the same in both the periods. In both the regression equations, the slopes are the same. So alpha 1 is equal to beta 1 in both the cases. So that means what you get is a parallel regression. If you get parallel regression scenario, this means that people may have changed the quantum of saving, but the basic behavior of saving has not been affected by the policy. So that can be the result here. But there is a third scenario, which is called the concurrent regression. Now, the concurrent regression is about the fact where the intercept is the same. So origin of the 2 curves are the same, but the slopes are different. So these 2 regressions have moved in the 2 different directions. And therefore, the behavior of the people have changed, but what the fundamental quantum has not changed. People are saving the same thing, same way, but same amount, but the way they are saving has changed. Their behavior towards the saving has changed. And now the fourth one is called the dissimilar regression. Now, dissimilar regression is a pure case of a structural change that has happened in the economy. Here, the intercepts are different because these two have two different origins, and the slopes are also different. So you can see that these two curves are going in two different directions. So their betas are also dissimilar. So they are actually absolutely dissimilar regressions. So now earlier there was something called the Chow test. The Chow test, what they used to do is that they will divide the data into two parts, before cutoff and the after cutoff, and they will run two different regression equations, and then apply a test to understand whether the intercept and the betas are different or similar. So that's what the Chow test used to do. But what dummy regression does is that it does not run two regressions. It actually runs one single regression. So you can see the regressions here, where it has been accommodated. The two regressions have been accommodated into one. And with a single regression, by constructing this dummy interactive dummy, that is D into X, it has been able to discern the similar results as the Chow test used to do earlier. So that's the advantage of the dummy regression here. So I'll just take you to the data now. If there is any question on the theoretical explanations which I provided to you.
Participants, you have any queries? Please ask if you have.
All right. So you can see here how the dummy has been created. So we have created, we have put 0000 from 1970 to 1981. And 81 is the period where something happened, some policy changes happened. And after that, from 82 to 1995, we have put 1. So that's how the dummy has been created. So we need one more variable, and that variable is multiplication of dummy into saving. So dx. So we have to create that. So we go to transform, compute variable, and then we are saying, okay, you give us dx, dummy into variate, and the argument built is that you multiply savings with the dummy. So this is how the interactive dummy has been created. So now you have the dx in front of you. So this is interactive dummy. Now we go to estimate the regression equations. We go to regression, we go to linear. We say, okay, dependent variable is saving. So we are analyzing the saving behavior. And then we are saying, this is our dummy. So beta 1. And then here dx, beta 2 for the interactive dummy. So these are the two we are calculating. We're saying, okay, model is good, f is significant, so we go to coefficient, and here in coefficient we find that these are the values that we got. This is for the interactive dummy, and this is for the simple dummy. So for interactive dummy, we find that the interactive dummy, simple dummy that we have created is significant, and interactive dummy is also significant. So if you remember the equation I showed you, the dummy was for understanding the differential intercept, right? Intercept of the two period. So if the intercept of the two period is significant, that means we are rejecting the null hypothesis that the intercept of the two periods are the same. So when this null hypothesis is rejected, this means the intercept of the two periods are significantly different. This is 0.06. So, it depends on you whether you take it as significant or you can reject also. You can say, no, I'm not going to accept it. So if you reject on the basis of the fact that is more than 0.05 by marginal amount, so you can accept the null hypothesis. Then in that case, we have to conclude that the intercept of the two periods are the same, right? So this means the origin of the two curves are the same. But if you look at the interactive dummy, it is significant. That means the slope of the two periods are different. So this means we are going to have a situation like concurrent regression, right? The two period has given us a concurrent regression, this one. So this is the result that we have in front of us. That means the saving behavior has changed, but not much effect on the quantum that has been seen. So here, if you look at, try and find out the average saving for the period, the first period, that is 70 to 81, the expected Y has to be where the dummy is put to 0, and then we have the variate. So if you put D is equal to 0 in the original equation that we framed in this equation, this is the equation alpha 0 plus alpha 1 dt. So in place of dt, if you put 0, and here in place of dt, if you put 0, then what you are left with is this alpha 0 plus beta 1 xt. This is the first equation that you are going to be left with. And for 1982 to 95, if you want to find out, then we have to put dt as equal to 1 in the equation. So if you do that, then you're left with alpha 0 plus alpha 1, beta 1 xt plus beta 2 xt. And this means that you're going to have alpha plus alpha, both the intercepts added together, plus this is the variate beta 1 and beta 2 added together. So this is going to give you the second regression equation. So if you divide, actually, if you divide these two into data into two periods from 70 to 81 and 82 to 95 and run a separate regression, you're going to get the regression like this, like the 1 and the 2. These are the two regression equations value you will get. So you can check that if you really want, you can check that. So alpha is representing the differential intercept, the beta is representing the differential slope. And this is the estimated equation. So if we try and find out, the first equation is going to be y is equal to 1.016 plus 0.080 xt. This is the first equation you get. A second equation, if you try and find out by putting the figures over there, you will get this equation, the second equation. If you want to check, we can divide the data into two parts and run separate regression, and you will see the same result appearing over there, right? So this is another application of dummy in front of you. Any question? No question?
Sir, I just have a doubt. When you were defining all this X, Y and all that in your equation, Y was savings, X was income. While you created the interactive dummy DX, you multiplied it with savings. Why? You should have multiplied it with X, right? Income. Why have you multiplied it with savings?
Okay.
Because Y was savings, X is income, T is time. Dummy was created as 1 and 0 for observations. I got that point. Interactive dummy was dummy into variable. That variant, that is. So that would have been X, right? X would have been income.
Yeah, so here I have not taken any covariate. It is actually the saving that has been analyzed. So X is representing saving over here. X is a variate, but it is representing saving over here. Oh, so I have wrongly written over here, I think. Why? Oh, wait a minute. Yeah. You're right. Y is saving, so it is a dependent variable, right?
Yeah, that is. So won't your DX have multiplication of dummy into income?
All right. You're right here. So let me You're absolutely right. I missed it. So saving is my actually independent variable. So it is not here. So, you know,
Income is
the
your
process will remain the same.
independent.
Yeah, process will remain.
Process will remain the same, obviously.
Yeah.
The process will remain the same.
Yeah,
It's
you are
just the
rightly
multiplication.
identified. Thank you so much for that. Thank you so much for that. So dx. So this is going to be income into dummy here. Yeah, so result may differ a little bit because
it might
the variant has
differ.
been changed.
Yeah.
Yes. So here the result is that both are insignificant. This means there is no impact.
Both are
no impact on here.
Yeah.
So this means there is no impact on of the event on the behavior of saving in both the periods. You're right.
Thank you, sir.
So this also shows how active you are. So I was thinking that people are not taking interest, but it looks like that you are very keenly observing the whole thing. Thank you so much. Yeah.
Thank you, sir.
Okay, so let's finish it off with one more example. So I'm going to data. Let me just use one more example and then we'll finish off this session. This is the quarterly sale that we have in front of us. So this is about the sale of durables like dishwasher, fridge, washing machine, and then this is the expenditure on durable items, total expenditure on durable item. So here, and it says sales for 4 different quarters, and we want to know how the sales differs in different quarters. So you can make out that this dummy has been created on the basis of the different quarter sales, right? So quarter 1, quarter 2, quarter 3, quarter 4, so something of this sort. So these sale figure is there. So 1 means quarter 1, so quarter 1, and rest of them are going to be quarter 0, 0, 0. So here quarter 1, quarter 2 0, quarter 3 is given 1, and this is for quarter 2, and this is for quarter 3, and this is quarter 4. So quarter 1 has been taken as a reference dummy, and this is how the dummy has been created. So dummy for quarter 2 was quarter 1 was given 0 and 2 was 1. Here 1 and 2 was 0, 3 was 1, and here 1, 2, 3 was 0 and 4 was 1. So that's how. So quarter has not been identified here as a column, but from the dummy you can make out there were 4 quarters data, and it has been. So simple analysis, we can go to regression, go to linear. If you are taking the analysis for any of it, let's say fridge, because fridge has got seasonality in data in sale. So a lot of seasonality you can observe. So how the sales in different quarters might differ for this. So R square is 0.4, F is significant, and here if you look at the result, the differential, the dummy 1, dummy 2 is significant, dummy 3 is significant, and dummy 4 is not significant. So this means that the sale is significantly different in quarter 2 and quarter 3, but it is almost the same. The quarter 1 and quarter 4 sales are the same, and quarter 2 and quarter 3 sales are significantly different from quarter 1. So that's the result in front of us. But here also we can use the covariate. So suppose we go to regression, linear, and then we add a variate here, like expenditure by the family on the total durables. And we can say, okay. So here in this case, the result will be slightly different when we add the X into it. So D2 is significant, D3 is significant, and D4 is not significant, and the durable expenditure is significant. So the sale is affected by the total expenditure on durable. Of course, that has to be significant. Quarter 2 and quarter 3 are significantly different, and quarter 4 is not different from sales in comparison to quarter 1. So the result has not been different. So even without using durable, we get the same result here in this case, but the result might change if we use the variant. But here in this case, it has not changed. So something of this sort. These are the applications of dummy. So I'm done. I have covered, I've started with data entry. Then I looked into chi-square test, the non-parametric chi-square test. And then I also looked at a little bit about ANOVA and ANCOVA model, how this can be framed. I also gave you a glimpse of how correlations are calculated by using the car sale data. Then I discussed the simple regression analysis with you, and also gave you a few variants of the simple regression model that can be estimated in terms of double log or quadratic. Then I started touching the multiple regression by using the car sales data, and we talked about collinearity diagnostic. And in the process, we also talked about heteroscedasticity problem for error distribution. And then I gave you a couple of idea in dummy regression. So this was precisely the coverage which was asked to me to deliver. And I hope I did some justice to all these topics and you learned few things. Of course, learning SPSS and learning statistics and regressions and all these things cannot happen in a couple of hours, but it's a matter of practice, and time and again you do and you become perfect. We can't expect anybody to be a master by attending 1 or 2 programs, right? So I hope you will devote time to it, learn by yourself, and do a lot of practice for learning. And I'll be happy if you get in touch with me and if I can be of some help to you. Thank you so much for this opportunity.
Thank you so much, sir. And as we are moving, towards the end of the session, so participants, do we have any queries from the participants before sir goes from here?
Sir, need your email ID, please.
Definitely the same question I was going to ask. Sir, आपसे contact में कैसे रहेंगे?
Okay, so let me just write my email over here. Can you see this?
Yes, sir.
Sir, and also we can share, we are having your mail ID, so we can always share your mail ID with the participants. So no issues.
Yeah, sure. So I have just written my mail ID here, so you can note it down. Right. We also do a lot of programs. So if you can just send your email and coordinate, then our people can get in touch with you, and you can, in summer, we are doing some intensive research workshop. So probably you can come and understand a little more on the multivariate analysis and all. This is my WhatsApp number. So if you can just drop in your email ID or WhatsApp number, we can get in touch with you and keep on informing about lots of programs that we do. Is that okay?
Sure, sir. Thank you. Thank you so much, sir.
Is visible to all of you?
Yes, sir.
Yes, sir.
Okay,
Thank you, sir.
Thank you. Thank you.
And participants will share the contact number of sir as well as his email ID on the on our participants groups as well. So
Yes, ma'am. Thank
yes,
you.
any other queries regarding the session, participants?
Sir, session was very good. Although we are very new in SPSS, especially me, I'm very a newcomer in SPSS. So today I got to know so much intense knowledge, and lately I will ask some other questions to you because I'm in the middle of some search and my writing paper and collecting of data. So definitely I'm going to ask some question to you, sir.
Yeah,
Thank
sure,
you
sure.
very much.
It will be a pleasure to if I can be of some help.
Thank you. Thank you very much, sir.
Okay, thank you so much, sir, for such an interactive session, and as well as as you have said that it is a long road to go, because in these couple of workshops we cannot unless and until we practice all together, we cannot have a real hands-on practice on SPSS. So sir, thank you so much, and for your words of wisdom, and as well as this enriching session on the topics you have covered, like simple regression and how to create dummies, multiple variations. So thank you so much, sir, on behalf of entire STTP organizing committee, as well as on behalf of entire IBMR IPS Academy. Sir, once again, it was our privilege to have you here in this STTP. Thank you so much, sir, and thank you so much, dear participants.
Thank you,
Thank you.
ma'am.
Thank you
Thank
so
you
much.
very much, sir.
Thank
Thank
you
you,
so much,
everyone.
sir. Thank
Kindly
Thank you,
share
everyone.
email ID. सर की email ID
Sure,
मैम जरूर
sure,
share कर
sure,
दीजिएगा.
sure. In the group,
Thank
I'll share.
Thank you, ma'am.
Thank you so much, sir, and looking forward for more such sessions in future. Thank you so much.
Yeah. Okay. Thank you. Thank you. Bye bye. Bye.
Please share feedback link also.
Yes, sir. And participants, so I'm just sharing feedback link for this session. And also, as far as tomorrow is concerned, tomorrow we are going to have session sharp start at 10 a.m. and tomorrow's resource person would be Dr. Vivek Singh Kushwaha, and he is going to take session on forensic finance using case study. So first two sessions he is going to take, and post lunch session we are going to have some hands-on practice on using R. So portfolio management using R, we are going to have our post lunch session by Mr. Pranavesh Chatterjee. So tomorrow morning we will be together meeting at 10 a.m. sharp for the session to be covered, forensic finance using case study. So thank you
ma'am.
so much. Thank you so
मैम
much,
आप
dear
मेल से शेयर करेंगी फीडबैक और चैट पे?
क्या
feedback.
चीज?
मैम फीडबैक फॉर्म आप मेल पे शेयर करेंगी और
I
चैट?
am sharing. I am sharing here in chat box also,
Okay.
and definitely I'm going to share in our WhatsApp group as well.
Okay, ma'am.
So do
Thank
not
you.
worry. Yeah.
Okay.